All right, great. Go ahead. Thanks.
So, hi, welcome to my talk about USB support in Zephyr OS. I'm a research and development engineer for Nordic Semiconductor. Zephyr contributor since 2016, right after Embedded Linux conference in Berlin. So one of my tasks is the maintaining of USB device support in Zephyr OS, but besides USB, I'm also interesting contributing to sensor displays, controls, and disk drivers and Modbus. Yeah. So I will generally describe what the current state of USB support in Zephyr is, what is what is the drawbacks that we have, and we'll shortly introduce new USB device controller API or device support I'm working on, and we'll talk about testing and USBIP. So our USB support is limited to a device stack only. We follow USB 2 specification, so we do not support super speed devices. So it's limited to high speed and full speed devices. We have support for well-known USB classes like mass storage controller, CDC/SM, or HID. Support composite configuration, and it's also possible to combine our built-in classes with user defined classes. Yeah, we have a bit poor high-speed support, and runtime reconfiguration of device configuration is not possible, and only one device controller instance is possible. Yeah, we do not support multiple USB controller device instances. Our current device stack is not written for Zephyr from scratch. It is imported and it is based on PC USB stack. Originally without any composite support, stack and classes revised several times. But at the end, the current design has many weaknesses that are anything easy to fix. So we decided to rewrite driver API and the stack itself. So, but yeah. Supported USB classes in Zephyr. We have audio class support, which is still experimental. I think we have good CDC/SM support, which is widely used. CDC/SM, EM, and RNT support. USB-DFU is a bit limited. It depends on MCU board, and yeah, USB HID. Sorry.
Sorry, Johan. I muted you by accident.
Okay. What are relevant USB samples? I think we have too much samples in Zephyr 3. Some of them are redundant, but we have that's a list of all important samples, and there's hyperlink behind. So if you have the presentation PDF, you can just click and it will forward you to this to the code in the GitHub. So we have few CDCSM samples, basic HID sample, accelerometer as HID mouse sample, which is unfortunately limited to an NXP sensor, but that can be easily changed to the other sensor device. We finally got mass storage controller sample to be more flexible and to work with RAM disk, flash disk driver, and SD card controllers, also over SPI. So let's talk about USB support in Zephyr in more detail. Here's an overview of the USB components. On the left is everything that's belong to host support, which is what we unfortunately do not yet support in Zephyr. And on the right is everything that belongs to device support. Typically, we have something like two communications channels. The one is configuration, and the other one is for data transmission. That is the purple one. Yeah. So these have this communication channels has different ranges in Zephyr or in devices that are based on Zephyr. We it's often necessary to have more information in the application itself about the states or if USB is connected or not. That's not the case, for example, on the host side, if it's the device connected to your Windows or the Linux host. How is device controller driver API organized in Zephyr? So API header for the device controller driver is located in include drivers as for the most drivers, and the driver serves in the driver directory. Here you can see the device USB headers, class headers. Some headers can be shared between host and device support. That it's not done yet. The only one class that has separate API and class definitions header, it's HID. Yeah. The reason is to be able to reuse USB HID defines in other subsystems like in Bluetooth. Yeah.
There's a question in the chat, Johan. Is it possible to runtime configure the reported US device ID? For example, device UUID.
I see that. So in the current USB device support, it's not possible. Yeah, it's I will that it's on my list. I will describe it later. Yeah, let's as renewal talk about important USB attributes, which probably everyone who has ever done something with USB knows. So we have endpoints. Which are device endpoints. Actually, only the device has endpoints. Yeah, device endpoints is source or sink of data, and endpoint address consists of direction bit, it's its most significant bit, and the number of the endpoint. The control endpoints are control endpoint are endpoints with the endpoint number 0. It's for out control out endpoint is the 00 in hex, and for in endpoint 80 in hex. Yeah. So every USB device has a configuration and at least one interface with 0 or more endpoints. So it's not necessary to have. It's not required to have other endpoints than control endpoints for USB device. For example, the USB DFU class doesn't have any endpoints other than controls. So, other important attribute is descriptors. They have device descriptor, configuration descriptor, interface descriptor, and endpoint descriptor. So the descriptors completely describe a device, a USB device, and the driver on the host side can obtain this information, all the information the driver needs from descriptor. Here you can see USB device support configuration overview in Zephyr. Each class in Zephyr must define USB configuration data that you see here in the middle in the yellow box, and an interface descriptor. Both, not both, so the USB configuration data structure will be placed in RAM section by a specific macro. The same happens with interface descriptor, and endpoint addresses and interface numbers will be fixed during USB device stack initialization. Yeah. You can also see here a lot of callbacks. Our entire current implementation of USB device stack is completely based on callbacks. Here on the left, class callbacks for the controller request, if the class supports controller request, that are with recipe as class, vendor, or custom handler. They have as a own structure for every endpoint with endpoint callback and as a status callback. Yeah. Any question to the configuration? Okay. We have a lot of redundant data here, variables, because, for example, endpoint address is also stored in endpoint descriptor, what we already have in the RAM, and it's stored twice. The other configuration is in the driver cells, which again stores endpoint address. and that we have that in many places, and it's a bit messy. Here an example how an USB descriptor looks like, that it's from a loopback sample, and yeah, just as example. Sorry. So let's talk. Let's go on level deeper to USB protocol layer. USB communication is completely driven by the host. USB device itself cannot initiate any communication. Yeah, we have in the protocol layer we have different packets, and the communication usually starts with token packets, which can be which is a start of frame, setup, out, and in tokens, and SF. So, for example, start of frame token consists of PID, frame number, and CRC. The nominal rate of SOF tokens is 1 millisecond for the full speed device and 8 times faster for high speed devices. So start of frame tokens helps to organize schedule, helps the host to organize or schedule the transfers. Other tokens are setup, out, in, which also consist of PID, but also address and point fields. So these tokens are directed to a specific endpoint. So out token signals data transaction to a function or device. In token signals a data transaction to the host. And setup token signals transfer, control transfer. Setup token has a superpower. So the host doesn't need to wait to the end of a transfer. It can issue a setup token every time. So the data packets follows token packets. The most important are data 0 and data 1 data packets, and they also consist of a PID and data field on CRC. And handshake packets usually follow the data packets, and the acknowledge packet, not acknowledged, and store. So the host self can never issue an not acknowledged or NAK. And as example, so if the device reply with NAK handshake for an out token, it means that it's unable to accept the data packet. And NAK handshake for an in token means that the device has no data to transmit. We can also halt an endpoint, and if an endpoint is halted, stall handshake will be sent to the host. Here, that it's a bit simplified diagram of USB host to device communication. It starts with start of frame tokens, and then the host sends setup token that is followed by data 0 token, and the device acknowledge that it's the green. So the blue one is from the host, and the green one is from the device. And Here you can see, for example, the device has always to acknowledge a setup token. It cannot stall at this point. It can still stall an endpoint if it doesn't support the request after an in token as alternative pad, or if it's not ready to transmit the data, respond with NAK. Yeah. Here that it's a control request. Wait-out data stage, and yeah, that is proper device enumeration. And here the start of the communication if device was configured with isochronous endpoint or the interrupt endpoint. And here as example, there's no handshake packet for isochron endpoints. It's always to be accepted, and here examples for interrupt and bulk endpoints. What happens in the driver and in the stack when a packet, for example, a Zephyr packet arrives? As I explained before, device stack architecture is based on callbacks, and if on an interrupt in the driver, an interrupt handler will be called, and for example, it's a new packet. Then in the USB device stack, a callback will be called, and in the stack itself is also another callback to the control transfer handler, which will read endpoint buffer and use memcopy. That's another user we have in current stack implementation that we, I think for all the driver have a static buffer, and we don't reuse the buffer that comes from the stack. We always copy that in the static buffer and in and back. And yeah. You can also see another issue here that during control transfer handling, for example, for set configuration for an interface, set settings for an interface or alternative settings, there is a need to call a code in a class or in specific application that again would start some USB or prepare some communication that one would lead to a deadlock, because everything here executed in the same context. It's for the most drivers, it is driver thread or work queue thread in the driver, and I think we have also few drivers that would execute everything here in the interrupt context. And as everything is based on callbacks, that it's not that easy to fix. And that is the reason why we decided to rewrite everything. Here's an example. We have that piece of code in many places in the tree. That's it's from HID samples, and these names endpoint read and endpoint write. Actually, it's USBDC endpoint read and USBDC endpoint write are very confusing for the users. And as it is more often in reports from user or customers. The code here has also few issues, and things here that this calls to the endpoint write do not respect a previous call. So it just this semaphore is given or taken. This semaphore is always given from GPIO callback, and yeah, if the buffer of the from the endpoint is busy, yeah, this endpoint write call will fail. Yeah, that's so the summary of the drawbacks in the driver library is that we have unreasonable event codes in the driver selves, like USB-DC configured, that's just misplaced because the driver never know if the device self is configured or not. There is no proper support for endpoint configuration, and so there is no support for multiple driver instances. We only support one driver at a time at build. Yeah, we have confusing API names like endpoint read and endpoint write. So endpoint stall and endpoint clear stall is a bit wrong because it's always halt. The stall is the handshake that device return to the host. And we do not have a proper support for endpoint request management and buffer management. And in the stack, we have a messy callback architecture. We don't have a proper management of the class instances. There is a lack of possibility to configure class instances at runtime to remove or to edit to the configuration. We do not have any API to set ID vendor, serial number, and BCD device attributes at runtime. So it's not possible to disable USB and call specific API to change, for example, vendor ID or product ID. The same for serial number. Everything is done during USB initialization is not changeable. We do not have a good notification channel to the application. So, for example, if how to notify application if USB is suspended or resumed. There's we forward these callbacks. The way in the current implementation to forward everything from the driver to the application, but it's in my opinion wrong. So we decided to rewrite USB device controller driver API and USB device stack. The drafts of the work are almost finished, and it will be published. It's on in a pull request. So my current plan is to have a new device support in parallel with the current USB device implementation for a certain period of time. Yeah, but that is something to decide in the API meeting.
Johan, there's a question. What is the roadmap timeline to revise this?
The timeline. It's probably affected by long time support release. So there's already a pull request to rework USB header and add chapter 9 as a proper chapter 9 header, but I don't think that will get in next time. There are a lot of things needs to be deprecated, and because of the how I understand that because of the LTS release, that will not be 2.7. Yeah. So I think so. My current state is that I have a new device controller driver API working with Nordic USB controller. I can dynamically add and remove class instances for loopback class that we use for test USB or with test USB tool from a Linux kernel. And I have draft for notification API, yeah, some kind of. Unfortunately we don't have in Zephyr something like GBus. Yeah, that we could use for some events like USB connected, disconnected, or suspended, and so on. So, but yeah. So I'm targeting 2.8 release. I think we will spend more time for to port or to rework all other classes, USB classes. Yeah, it's a lot of work. Yeah, here as overview, yeah, new USB device support. But we also have other necessary improvements in the tree. For example, USB mass storage class. This was imported from Embed OS, and that should probably completely rewritten, preferably with a separate CSI layer and also a counterpart of device SCSI subsystem, so that it can be tested or easily tested. Yeah, actually we don't have any tests for USB mass storage class in the tree, because there is no counterpart for that. And another class is USB DFU that depends on DFU image manager and partition layout. Yeah, that one should be more flexible and be usable with other bootloaders. And yeah, but DFU is small class. Yeah, it's easily to rework, and that would probably don't take that much time. But yeah, rework surface probably only makes sense for the new device stack, yeah. Because the DFU class has these two device descriptors, the one for runtime and the other for update mode or DFU mode. Yeah, and in the current approach, that is a bit hacked. This device descriptor switching after reattach event. Yeah. Yeah. Another thing, testing. Yeah, we don't have that much in the tree to test USB device stack. There is a test for the subsystem, USB subsystem, for the descriptors and driver API calls. There is we don't have any functional test selves like for control request or driver API calls like writes. Yeah, there are some, but they are only superficial. Yeah, it's just to check the input parameters and nothing else. Yeah, and another tool what we have for testing or debugging that it's sample subsys USB test USB that we use that with Linux kernel test USB tool. There are a lot of test cases for bulk interrupts and controls transfer as isochronous, but because of our current implementation of this function, it's only possible to test control and bulk transfers. But anyway, that it's very helpful for to test new drivers. Yeah? Especially, it's always a problem with the control transfers with zero link, package handling, and set halt and clear halt of an endpoint. Yeah. And so USBIP, we also have an driver called USBIP native POSIX, which is also a bit confusing. So, what is USBIP protocol? That the description and implementation of the protocol is available in Linux kernel. That passes USB device from a server that probably run Linux to a client over TCP. Yeah. It's based on also the data flow itself over TCP is based on ARPs from Linux kernel as USB request blocks. The current implementation in Zephyr can only be built for, as I said, for native POSIX, and is also currently in rework. Yeah. USB IP can be used to enable USB support for the platforms without any USB hardware. For example, yeah, like Chemo or POSIX boards. Yeah, but I think I never tried that, but it should be possible to build that on a Cortex M4 device that doesn't have any USB support, but network interface, and use that as a kind of virtual device controller. So what we need in Zephyr is for proper implementation is USB host controller API, and that it's current approach to test USB device controller IP on device stack. Yeah. Even without USB host support in Zephyr, we can probably use Linux for that for the first time.
Johan, there's a couple of questions in the chat. Have you tried the USB compliance tests? For example, Chapter 9 tests with the official USB CV tool. Will these tests pass?
Yeah, that depends on device controller. We do that at Nordic in regular with I don't know how often it's performed, but all the samples we have in the tree are tested on NAF devices to pass the USB CV tool. And the second question about stack support ISO transfers. Yeah, the ISO transfer is, as it depends again on it. The problem is not the ISO transfer. The problem is actually start of frame support in the drivers. Yeah. So, for example, audio class or audio sample uses ISO transfers, and that seems to work. Or that works on Nordic devices. Yeah. But that's, I never tested it on other devices. That Nordic, yeah, to be honest. So USBIP overview. That is the same picture as at the beginning of the presentation, and on the right is the device controller with USB device stack and controller driver. That could be, for example, a keyboard or a storage device, whatever, connected to an, that again here links what is USB IP server. That could be just a Linux host that exports this device over a network and over USB IP protocol to another Linux host that is a client. Yeah. And in the Linux kernel itself, the respective modules are USB IP virtual host controller interface and USB IP host or stub driver. And they can have the same or similar construct in Zephyr. Here. Here, everything what it's with blue background. Needs to be implemented in Zephyr. So the current state of this USB IP driver, that it's everything is mixed. There is no proper layering, but yeah, with the changes and host controller API, we could have a good test coverage on native POSIX or in QEMU for USB support. So USB support there's a draft pull request under GitHub, and didn't get that much attention, unfortunately. So USB host is still not supported, but USB IP would allow us a very good test coverage for both device and host support. And regardless of the host support progress, some partition functionalities will come as a part of device support testing. Yeah, some basic things like enumeration or some chapter 9 request handling will come in with device support as part of the testing. Yeah, I think that it's from my side. Any questions?
And regarding the schedule, the timeline, I just wanted to note that the 2.6 release was just released last week.
Yes. Yeah.
And 2.7 will be in the October timeframe, and 2.8 should be early next year.
Yes. Yeah. But The rework will not made in 2.7 because of LTS. Too much things needs to be deprecated, and there's still a lot of work to port all the class code to a new device stack.
Any questions for Johan? Okay, I'm going to go ahead and stop the recording. Thanks so much, Johan.